Hello and welcome to today's webinar. Thank you for joining us. My name is David Cash. I'm a member of the marketing team here at Mountz, and we've got a lot of information to run through today. So let's go ahead and jump right in to our topic today. But if you do have any questions, feel free to chat those to us, and we can do a time of questions and answers after the presentation and demonstration. So our topic today is 5 ways to improve process efficiencies and fastening automation workflows. And so that is a mouthful, and obviously we all know what repetition is. It's the act of doing something over and over, or seeing something over and over. And when it comes to fastening repetitions, there are some things that can happen or cause problems with the repetitive type of applications that we may see within the fastening process. So operators may tend to miss fasteners. They may cause additional errors just because it's so repetitive, and they may not be paying attention fully to the actual operation. And so if we can implement some types of workflows, this can help us to avoid some of those initial errors that we may see in that process. And so if you are a fan or a student of lean manufacturing, this may not be that new to you, but if you are new to lean manufacturing or some of the principles that are associated with that, if we take a look at this graph, you can see the dotted line is going to represent the capacity or the ideal throughput that may happen during the assembly process. And so the sine wave, or the actual graph that we have here, goes up and down around that actual capacity. And if we look at every value that is basically above the line, this is a Murray status. Again, this all comes from the Japanese teaching of lean manufacturing, and everything above the line is considered to be that which is an overburden or overworked or overused, and so this causes issues with the entire process, as there may be bottlenecks in the actual assembly process. And so everything that is below our capacity line is called muda, and this is waste. And these are some of the things that we try to look at and take care of within the process. And there are several different labels that go with the concept of waste, and whether it's the waste of transportation, moving one item to another location, or if it's waste of inventory, or the waste of motion, the waste of waiting basically on a component or a part, or the waste of defects. And so if we can, within our process, address some of these overburdens or overwork issues, as well as some of the waste elements to our process, then we can get closer to the optimal capacity for our particular assembly as it makes its way through the assembly process. And so as we look at the different workflow options and some of the advantages to looking and addressing some of those with certain types of tooling, that's going to bring us basically to our poll question for today. And our poll question, if we can go ahead and launch that, it's going to be, do you have multiple torque settings or processes steps in your fastening processes? And so we'll go ahead and launch that here, and I'll give you a few seconds to answer that, and then we'll move on with the rest of the presentation. Awesome. All right. For those of you who have participated in the poll, I do appreciate that. We'll go ahead and end that now. And it looks like we were roughly at 65% for yes, and 35% for no. And so, again, as we look at this entire process of workflow automations, when should we consider that, and how can we implement that, and where should we implement it? So if we're looking at different types of fastening, repetitive fastening tasks that we talked about during the open, if we need to try to increase production rates, if we want to try to increase our savings by reducing tool costs, if we are looking to optimize a workstation cycle time, or a workstation productivity, with that, improve our product quality, and overall enhance the process reliability, consistency, and efficiency within the assembly process. And so with that, that gives us a lot of different benefits that we can use with that particular type of workflow. And obviously the first benefit for that is that we get a streamlined manufacturing process. We help to eliminate the human error that comes along with that. With some of the different types of tooling as it relates to automation, we do get traceability type of information and data collection back from the tool itself. So there are a number of benefits, and we'll touch on more of those as we make our way through the rest of the presentation. Now, the 5 ways to improve the efficiency with workflows, again, they go hand in hand with some of the benefits. But the first one that we're looking at is going to be allowing us to error-proof the assembly process. Again, another Japanese manufacturing principle is the concept of poka-yoke, which allows us to design a process around the operator to help eliminate them making a mistake, or giving them the opportunity to make a mistake with the assembly process. And so if we can ensure that torque control is correct within that process, certainly that is going to be a big benefit for us. It's going to give us that ability, again, to have an intelligent process control throughout the fastening automation process. And it also gives us real-time monitoring of the fastening, or what's happening during the fastening process. And this also will touch on several areas that do overlap. But if there is an error, the error proofing process helps the operator correct the error right when it happens, as opposed to it being corrected further down the line, which can cause waste and more time and more money. So if we can error proof the fastening process first, this is really going to help us with the overall process. We can include the error proofing process with different types of line control devices and monitoring functions as well. And so the second key for the automation workflows is going to be the ability to have an automatic data collection process. And this allows us several advantages as it relates to being able to analyze what and how a process may be working. And so obviously we're talking about tooling today, and we want to be able to capture the fastening data that happens with the actual event data from a particular operation or an assembly. And if we have this data, this allows us to be able to document what is not only happening with the application, but we can also look at different things as it relates to the MURA between maybe different operators. You can look at statistics about maybe different shifts and how they perform on different days. and you can compare what the difference is between those data sets to help you make intelligent decisions about what is going on with the manufacturing process. So if we have that ability, we do have that ability to make data-driven decisions within the manufacturing process. And so if we have that, you have good information to look at. The third item here is going to be using a transducerized smart electric screw driving system. Typically, in all transducerized systems, there is a built-in sensor that is capturing the actual torque output that's happening during the rundown. Again, this is continuously measuring the torque in real time. And if there is, again, an error outside of certain parameters that we may set up, which is part of our process control, which is coming up next, then we're alerted. The operator then has the ability to correct it, then leading into our error proofing concept. So as we move forward, these are all kind of intertwined with each other. But having a system like that allows us, a transducerized system, allows us to be able to see what is happening because of the sensor that is built inside of the tool. It does then give us documentation and also traceable results from that tool as it's being used. The next one that I touched on there is going to be process control. And so we can assign a set of standards to a certain process, and the less that the operator has to do or think about within that process is going to be a great advantage for that process control. As it relates to fastening, we want to be able to program assembly processes or sequences. This way, the operator just goes through and does the proper tightening that they may be needed to do, and they don't really need to think about anything else, or they don't need to rely on themselves basically to change a preset or grab another tool. If we have all of these things included within the process control, then that's going to help us there. And as it relates to fastening, if we do have tolerances that can be set for each specific fastening or fastener, that is going to help within the process. And finally, we could have multiple fastening tasks set up throughout that particular assembly. Excuse me. And then we can help to minimize the number of workstations that may be able to be consolidated as we look at the ability to use a DC type of tool that has multiple presets where we can eliminate possible different workstations. Again, helping with the muda, the waste that may be happening because we may not be using a specific tool to its full capacity or capabilities. And if we have, for example, a standard electric clutch tool or even a standard pneumatic type of tool, those typically are going to only have one torque setting. And so with that, we could have multiple tools be able to replace one separate multiple workstations and consolidate that into one type of workstation. And so this is kind of an example of that, where we have 6 different stations, and we can use the range throughout this tool to accomplish that and have us at one workstation using a DC type of tool for that. And then the last component is going to be the fastening automation. And the fastening automation, again, goes hand in hand with the error proofing, the process control, but it does allow us to create different assembly automations to help the operator not necessarily, again, make a mistake within the process. We can help to replace manual processes within the actual assembly. And because the the DC tools do have the ability to communicate digitally with other types of feedback. They can communicate with PLCs. It could also be integrated with additional line control devices. So with that, we can also control where the tool operates based off of location with certain types of other fastening equipment. So we can create, again, fastening automations within the actual assembly process. And we'll do that here in just a second in the demonstration part of it. But this is again, the 5 keys that we're highlighting. The first one, again, is error-proofing the fastening process, having the ability to be able to automatically collect and analyze the fastening data, using a transducerized tool that is going to be measuring the actual output of the tool on the application, in placing process control within the assembly, and finally having assembly automations within the actual fastening assembly itself. And so why or how can a DC tool help with the workflow operations? Well, let's go ahead and jump into our demo portion of this, and we'll take a look at a number of different scenarios and how the different settings within the tool can help us go ahead and create or solve a certain problem within the assembly as we look at them. So let's see here. So our first one is consolidate workstations, or we're solving the problem of muda, which means that we have multiple different workstations. We touched on that a little bit within that, but if we take a look at the tool itself, so on our screen here, you can see our ECTD system, which is our transducerized DC tool. And on here, you can see we have our presets. We can use a multiple of different presets within the range of the tool that we're working with. And so we have 15 available presets that can be used. And then we have 2 special multi-sequence processes that allow us to stack different presets on top of each other. So this gives us the ability to be very flexible within the operation of our assembly. And so if we do have workstations that are just using 1 or 2 drivers at one particular location, obviously we may be able to consolidate that and use the same application or same tool with different torque settings within the range of the tool for us to be able to consolidate and possibly use those resources where they can be deployed and be more useful. This can also, again, help save in tooling costs because we're only buying 1 tool, and that way we're replacing other tools, even though they are less expensive. The flexibility that we do get with that in replacing the right number of tools obviously gives us a benefit for that. So that would be consolidating a workstation. Now, the next scenario is, let's say we have a fastening bottleneck type of scenario where we may be dealing with a situation where we have a fastener that is fairly long. This fastener is at a lower torque range for our specific tool, and we want to be as accurate as possible. And through testing, we found that a high RPM for this particular joint gives us some really inconsistent numbers because as we're trying to use a light type of torque, having too much RPM creates uncontrollable inertia within the fastening process. So we need to go at a slow RPM. And in this case, we have our fastener here and it roughly takes about 4,500 degrees of rotation to run this down. So if we go to our preset here, we're looking at about 1 Newton meter of torque. And if I go ahead and run this down, you can see that it is very slow. It's taking quite a bit of time for us. And we want to make sure that we are being as accurate as possible for this particular fastener. Now, in this case, this took almost 9 seconds to run this fastener down. And so obviously, if we're doing multiples of these just in a few fasteners, we're adding additional time to the assembly process. And if our goal is to help to increase production and be as accurate as possible, we do have the ability to use a strategy which we call our free speed and also free angle. And so in our fastening tab here, down below in the bottom section here, we have our free angle and our free speed. And what this does is it allows us to be able to turn up the RPM of the tool for most of the rundown, and then the tool will then slow to the running RPM here at 100 RPM. And so with our fastener taking roughly 4,500 degrees of rotation, let's go ahead and we'll run it 3,800 degrees let's just do it at 500 RPM. And this is going to help us to be a little bit more efficient during this process. And so if I go ahead and run the next fastener down, you can see there we gained nearly 6 seconds in our total time. And this also gives us the slower RPM at the tightening or torquing part of the rundown. So this helps us to be able to solve that fastening bottleneck, again, which is a mirror, and this is the overburdened or part of the fastening that we needed to move a little bit closer to the capacity line. All right, the next scenario would be a muda or a waste if we do have cross thread issues with a particular fastener. And to do this and help solve the cross thread type of problems that we may run into, we can use a strategy as again within our programming of our preset, and that would be done in our advanced tab for a specific preset. So let's go ahead and use preset number 2. If I want to program a preset here within the image, you can see that I'm working with preset 1 of 15. If I go ahead and I tap here, we can go ahead and we can select which preset we want to use, and we can now use for the cross thread issue, which would be our free reverse and free rotation. And what this does is it allows us to basically start the fastener in the reverse direction for a certain amount of turn within a certain amount of RPM to help that first thread kind of drop into the assembly, and then we go ahead and move into the fastening direction. And so with our free reverse rotation speed, we can set that fairly low at 75 RPM, and we can do that for 7/10 of a turn. And now for preset 2, this will allow us to do that as we do that fastening process. So I can come back in here and I could select preset 2. Now we're working at preset 2. And what you'll see here is that the fastener will actually, again, just like we've talked about, it will start in the reverse rotation, and then it automatically will go to the running torque here, and we'll go ahead and shut off once torque is achieved. And so we do have a couple different videos on how this actually works with a little bit more detail, but this can help against the cross thread event that may happen with any type of fastening with a finer thread. All right, so that one basically is solved. Now let's talk about how we can error proof the fastening for a particular fastener. Now, one thing that we just worked on was helping to mitigate the cross thread issue. But what happens if we want to try to detect if there was a cross thread issue? And so we can do this if we jump back into our menu here and go to our fastening tab. If we look at preset number 2, we do have the ability to not only reach a certain target torque, so in this case 1.75 Newton meters, but we can also monitor the amount of turn or angle that happens within that process, helping us to detect certain types of errors and be able to then go ahead and fix those right now. So if we have a minimum amount of turn or minimum amount of angle that must be met, we could enter that in as a window. So in this case, these fasteners are roughly about 2,500 degrees of rotation up. So let's say that we want to make sure that we have at least a minimum of 1,000 degrees of rotation. And then we can also guard or check for errors if there are any type of over torque, or excuse me, not over torque, but stripping fasteners by creating a maximum amount of turn window as well. So let's say if it goes farther than 3,200 degrees of rotation, then we would receive an error as well. So not only are we have a limit over the torque, but now we also have the ability to monitor the amount of turn that happens, again helping us to implement a workflow that's going to alert the operator if we have a fastening issue. So if we come back out on preset 2, if I go ahead and run the fastener down, great, we were at our window of our actual rundown here. And so if we had example, let me go ahead and go back to one that we've already torqued, or let's move this one down just a little bit. So we're going to be within the threshold. If we had a cross thread type of an event, that's going to happen right at the very beginning of the fastening. And so we must meet at least that 1,000 degrees of rotation. If we don't, then we're going to get an error with that. Again, letting us know, alerting the operator that the fastening that we just did, there was an issue, and we need to go ahead and address that issue. And so those are things that we can do to help error proof the actual fastener within that process. Now, there are other things that we can do that we talked about as well, that you can use a position control type of arm that will allow the tool to only be in a operating state at the correct fastener within the process. We'll touch on that a little bit more as we look at our last scenario here, and that's going to be our automate the actual assembly process. And so in this case, let's think we've got a multiple torque values that we're dealing with throughout our assembly process. And so with that, we can use what's called our model function. Now, we can have up to 15 models, or basically assembly jobs, within the use of the 15 available presets that we have. So to do that, we can go ahead and we can enter into our menu. We can go into our controller here, and let's go ahead and put the system into the model mode. And then we can come down here to our model, and we're again dealing with model 1 of 15. If we want to change to a different model, we could do that here, and we would select that particular model. For each model that we have the ability to have 20 different steps that we can use throughout that model. And so there are different things that we can do within the model. So in this case, we're going to do just a very simple one. We will select our operation. And in this case, we can do a fastening. We could also do a delay. We could use our digital inputs and outputs to communicate with locks or line control if we need to reorient a part within a locked jig type of system, or we can also include a barcode scan in here as well. But let's go ahead and we'll make this pretty rudimentary. We're going to do a fastening step. We can then call out which preset we want to use. So we can use preset for a certain count. So let's go to preset 3. We can enter that, and then we'll use that for a count of 1 just to make it easy. Next, we'll do another fastening step. We'll do preset 4 for a count of 1. Sorry. Count of 1. And again, we'll do another fastening on preset 5 for a count of 1. And then if we like that that model, we can go ahead and we can come back out. And now what you'll see is the screen has changed. Because we put the unit into the model mode, we now have the ability to select models 1 through 15. And again, the 15 models can be comprised of the 15 different presets that we have available to use. And so what you'll see here is that we are using preset 1, or excuse me, we're using preset 3. This is our first step within the model, and it is a fastening step. And so we go to our fastening location, and we can go ahead and run that fastener down. And if we get an error like this, then we can go ahead and we can reset that fastener. And I must have a setting in here on preset 3 that is allowing, yes, we have preset 3. All right. Well, this is certainly not advantageous for our demonstration. Let's go to preset 1. All right. Okay, so now it has changed up here. We are now using preset 1, step 1 of our fastening. Now it has changed to preset number 4. And now we've changed to our final preset, which is preset number 5. And now our model is complete, and we can go ahead and run that again. If, for example, we have a part that comes through and maybe it has a different model associated with that, and we want to allow the operator to select which model is going to be used by the use of a simple barcode scan. We could do that as well with the use of a barcode reader connected to the RS-232 port. We can then select that particular model just by a scan of the part. And now you can see that it has changed that model to model 1 that we were just working with instead of model 7 that we were on. And so that again gives us the ability to help remove the operator from having to interface with the controller, allows them to work through the assembly process, and helps us with our workflow automation. Now, there are a number of other features that we could go through, but we don't want to spend too much time with that. But if there are certain challenges that you may be facing, we can certainly look at what types of strategies that we might be able to have within our systems and tools available to us to be able to help with those different fastening automation workflows. And so with that, it's going to lead us to the end of our presentation. We're going to now go to any questions that you might have, and I'll do my best to answer those as I grab a drink of water. Chris, do we have any questions?
Morning, Dave. The first question we had is, let's see, can the system be programmed and used for like a thread tapping application?
It certainly can. There are a couple of different strategies that we can use for a thread tapping type of mode. If you have a scenario where the cutting torque, or maybe you need to run through a certain patch with the fastener, it does allow us to be able to increase the torque during a certain portion of the thread cutting, and then drop back down and look for a seating torque. And then we also have a special thread tapping mode as well. So yeah, there are different strategies that we can use for a thread tapping type of application.
All right, Dave. Thanks. Next question we had was, is this system compatible with an MES system?
It certainly is. Now there are, as we mentioned, there are digital inputs and outputs. Our ECTD product does have the ability to communicate with different MES systems. We do have the ability to network the controller either through the RS-232 port, or there is also an Ethernet port and also a 25-pin IO port as well, where we can communicate with different devices such as an MES system, PLC, and other line control devices.
All right, thanks, Dave. Next question is, how many tools can we use with an individual controller?
So with our ECTD product, there is one tool that's connected to one controller. If you are looking for a scenario where you want to use a wireless or a battery system, battery tool, a transducerized system, we have that as well, where we can connect up to 8 different tools to one controller. So there are some advantages that way with the wireless system. With this system, it's one tool and one controller.
All right, Dave. And then the follow-up part on that wireless one is can the wireless tool be used with the system you were showing, or is that a different type of controller?
It is a different type of controller. However, all of the functionality is the same. between the different controllers. Now, there are some unique things that are different about the wireless controller versus the corded controller, but those deal with how those particular tools work and function. But they don't differ as far as the number of presets, how you can program those, how you can detect any type of errors that you may be looking for within the fastening process. So they are identical kind of across the board with some special functionalities for each type of tool.
All right, Dave, thanks. Next question was, what is prevailing torque, and can the system be programmed to use this type of application?
So prevailing torque would be a situation where as you're turning or running down a fastener, say it's a lock washer, or excuse me, a nylon lock nut that has a safety feature on that. As we're running that down, that will typically take up some of the final torque that's being delivered, because it is using some of that torque to actually cut that nylon lock. So in this case, with the prevailing type of torque, what we can do is we can account for that cutting. We can tell the system during the thread engagement portion of the rundown, look at the torque value between this degree of angle and or X degree of angle and Y degree of angle, give us what that value looks like, and then add that to the final torque that we need to achieve to be able to get the correct stretch or stretch compression on our fastener. So that is part of the ECTD plus version, where we can account for a prevailing torque within the actual operation.
All right, Dave, thanks. And it looks like that's the last of our questions for today.
All right. Thank you so much for joining us. And we look forward to seeing you next month. If you have any questions about this topic or about our DC tool lineup, feel free to give us a ring. You can reach us through our website. We also have an application team as well that can talk to you about your specific application. With that, thank you again so much, and we'll see you next time.